Last time we built a neural network, layers of matrix multiplications with ReLU in between. We said it learns through gradient descent, compute the gradient, update the weights, but we skipped the hard part. How do you actually compute the gradient when you have hundreds of layers and billions of parameters? The answer is one algorithm, backpropagation. It's the most important algorithm in modern AI, and it's just the chain rule from calculus. Let's start with the chain rule. If y is a function of u and u is a function of x, then the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. Simple example. Y equals u squared and u equals 3x plus 1. Then do is 2u and do dx is 3. So do dx is 2u times 3, which is 6u, which is 6 times 3x plus 1. The chain rule lets you differentiate compositions of functions, and a neural network is nothing but a composition of functions, layer after layer after layer. Let's compute backpropagation by hand on the simplest possible network. One input x, one weight w1, one real u, one weight w2, one output. The forward pass h equals w1 times x, a equals real u of h, so a equals h if h is positive, 0 otherwise. Y hat equals w2 times a, the loss L equals y minus y hat, all squared. Now let's go backward. We want dl slash dw1 and dl slash dw2. How much does each weight contribute to the error? Start from the loss. dl slash die hat, the derivative of y minus y hat squared with respect to y hat is minus 2 times y minus y hat. With our numbers, that's minus 2 times 3 minus 1.5 comma, which equals minus 3. Now die hat slash day. Since I hat equals w2 times a, this is just w2, which is 1.5. By the chain rule, dl day equals dl slash die hat times die hat slash day equals minus 3 times 1.5 equals minus 4.5. Next, dej, the derivative of ReLU. If h was positive, it's 1. If h was negative, it's 0. Our h was 1, which is positive, so day dh equals 1. So dl dh equals dl day times day dh equals minus 4.5 times 1 equals minus 4.5. Finally, dh slash dw1 equals x, which is 2. So dl slash dw1 equals dl dh times dh slash w1 equals minus 4.5 times 2 equals minus 9. And for w2, dl slash dw2 equals dl slash die hat times die hat slash w2 equals minus 3 times it equals minus 3 times 1 equals minus 3. Now we update. With a learning rate of 0.01, new w1 equals 0.5 minus 0.01 times minus 9 equals 0.5 plus 0.09 comma equals 0.59. New w2 equals 1.5 minus 0.01 times minus 3 equals 1.5 plus 0.03 comma equals 1.53. Both weights increased. That makes sense. The prediction was too low, so the weights need to grow. Let's verify. New prediction is real u of 0.59 times 2 times 1.53 equals 1.18 times 1.53 equals 1.81. The old prediction was 1.5. We moved closer to the target of 3. The loss went from 2.25 to 1.42. One step of backpropagation, and we're already better. What we just did by hand, a computer does automatically using a computational graph. Every operation in the forward pass, every multiplication, every addition, every real u is recorded as a node in a graph. The backward pass just walks this graph in reverse, applying the chain rule at each node. This is what PyTorch and TensorFlow actually do under the hood. When you call loss.backward in PyTorch, it traverses the computational graph and computes every gradient automatically. No human does this by hand for 1 billion parameters. Here's why backpropagation is genius. Without it, you'd need to compute each gradient separately. For n parameters, that's n forward passes. Way too slow. Backpropagation computes all gradients in just one backward pass. One forward pass, one backward pass, all gradients. The cost of the backward pass is roughly twice the cost of the forward pass. So training is about 3 times the cost of inference. For a model with 1 billion parameters, that's the difference between feasible and completely impossible. Backpropagation isn't perfect. Remember, the gradient is a product of local derivatives along the chain. If those local derivatives are all less than 1, the gradient shrinks exponentially as it travels backward. In a 100-layer network, if each local derivative is 0.9 comma, the gradient reaching the first layer is 0.9 to the power of 100. That's essentially 0. The first layers stop learning. This is called the vanishing gradient problem. It's why deep networks were nearly impossible to train for decades. And it's why RealU was so revolutionary. Its derivative is either 0 or 1. When it's 1, the gradient passes through unchanged, no shrinking. This simple fact unlocked deep learning. So that's backpropagation. The chain rule applied systematically through a computational graph, computing all gradients in one pass. It was first applied to neural networks by Rumelhart, Hinton, and Williams in 1986, and it's still the backbone of every AI training run today. Next time, we'll look at loss functions, the different ways AI measures its own mistakes, and why choosing the right loss function is as important as choosing the right architecture. Subscribe if the math is starting to click. See you in the next one.